So make sure you return.
I just turned it on.
Okay, so there's only one bar, which means it will die before the
lecture ends.
Okay.
Okay, thank you. So am I audible in the back? Okay, I'm Ruta Mehta. I'm co-teaching this course with Chandra. I'm also in computer science department. I joined in January, so I'm pretty new here. And it's exciting for me to teach this class, some part of this class, and I'm going to start with randomized algorithms. Okay, so today we'll start with some introduction and some algorithms. So I think randomization is very powerful. Whatever you do, right? Whether you are playing rock, paper, scissors, okay, or you are calculating insurance, or you are trying to kind of decide on risks of multiple things, right? So suppose, let's say we play rock, paper, scissors. Who wants to play with me? Okay, okay.
Wait, on shoot
or three? On three. Okay, you knew. Okay, sorry. Okay, so what are we doing? He kept playing rock, 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 and I knew that he's going to do that, then I started playing pepper, right? And if he kept doing that, he would lose. So he has to randomize. Right? If I know his strategy, I'm going to win. And same for him, right? If I keep playing scissors, then he will keep playing rock and beat me, right? So randomization is important, even in the small thing as winning in rock, paper, scissors, okay? So today we will see some basics of probability theory, randomization. Like what is probability space, expectation, events. So we had posted a preliminary kind of prerequisite type of slides on website and on Piazza, and I hope you have gone through that. So I will expect you to know those things, but I'll brush up on them, okay, very, very fast. And then we'll see what are the randomized algorithms, what do we mean by that, randomizing in an algorithm. Okay, and then we will see an example of QuickSort and its randomized QuickSort and its analysis. Okay. So what is an algorithm? It takes an input. So far we have seen algorithms which are deterministic, which takes some input, gives some output, does something inside, right? In the randomized algorithm, in addition to taking input, it also kind of generates some random bits to decide what to do inside the algorithm. Okay, and then output something. And so the output is somehow dependent also not only on the input but also on the random bits that it uses. Okay, so let's take an example. So you might have seen the QuickSort algorithm. What is QuickSort? It's like you are given an array of numbers. Okay, they may not be sorted, and you want to sort them. There are many ways to do that, but one of the ways, which is called QuickSort, is you pick an element, say first element. Okay. It may not be the smallest one. So you try to find its position in the array. So you compare it with every element. You try to find all the elements which are smaller than this element, all the elements which are bigger than this element, and all the elements which are same as this element. And then put all the elements smaller than this element before it, and all the elements bigger than this element after it. Okay? And then you recurse on these smaller and bigger element sets. Okay? This is the QuickSort. I'm just recalling the QuickSort algorithm. Okay? Now here, you are in every iteration, you are choosing a pivot. So either you choose this pivot deterministically, like I always choose the first element as the pivot in the array, or you do it randomized. So you pick an element uniformly at random from the array. Okay? Now, why would you want to do that? So suppose I am running deterministic QuickSort and my array is sorted already, but I didn't know that. That's it. And I'm always picking the first element. Okay? What would be the running time of it? So when I pick the first element, when I have n elements in my array, I pick the first element, I compare it with every element, and then realize, oh, well, this was the smallest. So first position was its right position. And then I'll have only the larger elements than this, right, left out to be sorted. And when I do the recursion, so I did n comparisons, and now I'm left with n minus 1 array to sort again. Right? So again, the next time when I try to pick the first element in the n minus 1 array, again I'll take n minus 1 comparisons. Okay? So n plus n minus 1 plus n minus 2 and so on. And you know the recursion, the formula for this, right? It's just n square. So in the worst case, deterministic QuickSort can take n square time. But when we do randomized QuickSort, now because we are doing randomization, we have to talk about expected running time. And we will see what that is. But we can show that the expected running time, worst case, is order n log n for randomized QuickSort. But one point to kind of understand here is the expectation is n log n. Okay? There may be some tiny probability with which it can still take n square time. Okay? Another example, suppose I want to multiply two matrices, A and B. Okay? And I want to create C matrix. What is the brute force way of doing it? Just multiply the two matrices. Right? And what time does it take? N log n. I just brute force, like simplest thing. Take the first column of the A, first row of the A, multiply it with the first column of B, and cube. And there are faster, very clever algorithms which has brought it down to 2.37. And there has been a lot of work on this. Okay? Now, if the n is very large, this is still a huge number, right? Now, let me give you a randomized algorithm, which you pick an n-dimensional vector r uniformly at random, and look at the quantity a times b times r. Now, I can compute a times b times r without computing a times b. How I first compute okay, the pointer is not working, sorry. I first compute b times r, that will generate a vector that takes n square time. Then I compute a times r, a times that vector, right? Again n square. And then compute c times r and check whether they are same.
So I think you didn't say that you want to check AB equal to C, right?
Yeah. Yeah, I want to check whether AB equals C. Okay? And so what is the running time of this algorithm? Order n square. But will I get the correct answer always? So if AB was C, so what I will do is I'll pick this random vector, I'll compute this quantity A times B times R and C times R. If they are same, I'll say yes. Otherwise, I'll say no. So the running time of this algorithm is n square, order n square. Right? And it will give a correct answer if indeed AB was C. Right? But if AB was not C, then I claim that it gives, so believe me that it gives me answer correctly with half probability. Yeah, so let's not go into that right now. But suppose it gives me answer with correct answer with half probability. Okay. Now this is a not very good probability of getting a correct answer. Okay. But what if I repeat this procedure 100 times? And every time I get yes, 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 yes. Then what is the probability that I am not getting a right answer? That AB was not C and still I am getting AB equals C. All the 100 times. This turns out to be, because every time I am picking a random vector, it is 1 over 2 to the 100. So I'm just saying that if you have a randomized algorithm which has one-sided error, okay, and with some probability it gives a right answer, then you can repeat it with independent random bits and boost the probability of getting the correct answer. Yeah.
Is there some regulations to choose the vector? I mean, for example, it 0, 0, 0, 0, 0, or 1, 1, 1, 1.
No, that's why I'm saying pick a random vector. Okay, so if suppose all the I can restrict it to say I am picking it from 0, 1 to the every entry in the R is between 0 and 1. Okay. So why randomized algorithm? So already we saw that it has power. Okay, it can give you simple algorithm, fast algorithm. Even though there may be some getting a probability of not getting a right answer, you can do something to boost the probability of getting right answers, right? So it has many applications in algorithms. Data structure, for data structure we'll see some applications later in the next week. In some cases, randomized algorithms are the only algorithms known. Okay, fast algorithms. They are efficient and they are simple and they have some deep connections with mathematics and physics, and in general they are lots of fun, right? Okay. So another point is that there is a difference between kind of analyzing a randomized algorithm and analyzing a deterministic algorithm on random input. Okay, so if we have a deterministic algorithm, we can either ask for its worst case complexity or we can ask for its average case complexity. What is an average case complexity of deterministic algorithm? That your input to the algorithm is coming from some distribution. And then you ask what is the expected or average running time of this algorithm according to this probability distribution. Okay, so on every input, the algorithm deterministically gives us output and takes some running time, right? Like QuickSort took, like in some input it takes n square, order n square, in some input it can take n log n. Okay, so you take the average of this running time. Average meaning you multiply the running time of the input with the probability of getting that input and sum them up. Okay, so that expected running time is the average case analysis kind of. You look at the expected running time where the input is coming from some distribution. But when we talk about analysis of a randomized algorithm, now the input is worst case, okay, but algorithm is generating some bits, like in the multiplication of two matrices and checking whether it's C, the generation of the vector R was the randomization algorithm used. Okay, so algorithm uses random bits in addition to the input we saw, and then we ask for the average performance of the algorithm as per this random bits used by the algorithm for every possible input. Okay, and take max out of it. Okay, so I just want to point out that there is this fundamental, if you have seen average case analysis, then that is different from doing analysis of a randomized algorithm. Okay, and we will formalize this. Okay. So before we kind of go into kind of doing a formal analysis, I want to set up the kind of notation and the language that we speak to analyze randomized algorithms, or language of randomization. Okay? So when we talk about randomization, there is some probability space involved. Let's say, and we are going to talk about discrete probability space. Okay, so the number of elements in our probability space are always finite for now. Okay, so let's say omega is our probability space. Every element in this omega is called elementary event, and there is some probability associated with every element. Okay, I'll use element and elementary event interchangeably. Okay. And because it's a probability, the sum of all of these probabilities should be 1. That is what its probability is, right? You are picking some element from this space, and you are picking one element, so, and with some probability, right? So the sum of the probability of picking all the elements is just 1. Sum over all the elements is 1, right? So what is the example? Suppose I am kind of tossing a coin, and it's unbiased coin, and the two possible outcomes are heads and tails. Okay, so that's my space. Those are the elements, heads and tails. Okay, and for every element, because it is unbiased coin, with half probability it will come out heads, and with half probability it will come out tails. Okay, or suppose I am rolling an unbiased dice, 6-sided dice. Then the outcomes are 1, 2, 3, 4, 5, 6, and for every outcome the probability is 1/6. So simple, right? You have seen this, all of these before. Now event is a subset of elements or elementary events. Okay, and then you can talk about the probability of an event. So suppose A is one event, then the probability of this event is just summing up the probability of every element in this event. And the complement event is just all the set of elements which are outside this event. So let's take an example. Suppose I am rolling 2 dice. Okay, and an event happens if the sum of the 2 dice, the sum of the numbers that comes up on the 2 dice is even. Okay, so how many times would this happen if? So what are the when would the sum be even? When will that happen?
If you are odd or 2 or even.
Exactly. Right? What are the other possibilities? Odd, even, even, odd. Right? So what is the probability that the sum will be even? How many elements? So there are 36 possibilities, right? 6 possibilities for the first die, 6 possibilities for the second die. Total 36. How many of those will give me even number for the sum? 18, right? So size of A is 18, right? And for every element, it's the same probability, 1/36, because these are unbiased dice. Right? So for this event, the probability is 1/2. Two events are called independent if the probability of happening both of them is just the product of the probability of both. So if I want to ask what is the probability that A and B both happens together? And if it turns out to be probability of A times probability of B, that means they are not affecting each other in some sense. Okay, and then they are called independent. Okay. So let's take an example. Flip 2 coins. Let's say A is when first coin comes out heads, and B is when second coin turns out to be tail. What is the probability of A intersection B? What is the probability that first coin turns out to be heads and second tails? It's on the board. It's on the projector actually. So you don't want to say it, or? 1/4. Right? And what's the probability of A individually and B individually? Half. So they are independent, right? Because 1/2 times 1/2 is 1/4, right? Now suppose A is that both turns out tails, TT, and B is the second turns out heads. Now what is the probability of A and B? 0, right? But probability of A or probability of B both are non-zero. I mean, probability of A and probability of B both are non-zero, right? So these are independent or dependent? Dependent, right? There is a very simple union bound which is for events. So if you have 2 events and you ask what is the probability of happening either of the 2, okay, it is upper bounded by the probability of sum of the probability of both. So if E and F are 2 events, probability of E union F is probability of E plus at most probability of E plus probability of F. And it's very simple to prove, right? Because what are the elements in E union F? Are all the elements which are in either in E or in F, right? So it's just this simple formula. And if this is at most, because E and F can have intersection, right? So here in the first expression you are counting it only once, but in the second expression you may be counting it twice, and that's why less than equals. Okay? And this is useful very much actually. This simple formula actually. There is another very powerful tool which are random variables. So in a random variable assigns a number for every element in the probability space. Okay, we will see why you would want to do that. Okay, and then you can ask for what is the average number you get according to this probability distribution for this random variable. So this average, or we also call it expectation, they actually just call it expectation generally, which is just the probability of, so you sum over all the elements in the probability space, probability of that element times what is the value of that element as per this random variable. Okay, so just we are taking an average as per the probability distribution for this variable. So let's take an example. You again roll a dice, 6-sided dice, and let's say my random variable is x. So okay, it started working good. Xi is I mod 2. So xi is either 0 or 1, right? And now if I look at the expectation, how many times can xi be 1? When will xi be 1? When I is odd. And that's 3 times. Right? And probability, so here xi is either 0 or 1, and probability of I is 1/6 every time, wherever it is 1. So the expectation is half. because xi is 1 3 times. Right? Another example, suppose another random variable yi, which is just I square, and if you try to calculate the expectation of this, is just 91 over 6. It's just I square divided by summation of I goes to 1 to 6, I square divided by 6. Okay, and it will turn out to be 91 over 6. Simple mathematics. Now let's try to use it to do something non-trivial. So suppose I have a graph, undirected, okay, and I'm going to delete every vertex with half probability. So I go over every vertex one by one. I pick a vertex, toss a coin. If it turns out to be heads, I delete it. It's an unbiased coin. Okay? Otherwise, I keep it. So with half probability, I am deleting this vertex. Then I go to next vertex and so on. I do this with every vertex. Now I'm asking, what is the number of, and let's say H is the resulting graph after I'm done with this. So as soon as I remove vertex, I have to remove all the edges incident on it. Okay? Now, what is the expected number of vertices in H?
Number 2.
Why?
It's for each vertex, there's a 50% chance to be removed.
Okay. So how did you get n over 2? What did you use to make this conclusion?
The probability of the vertex remaining by the number of vertices.
Why is that?
Use the formula in the last slide.
Okay. Let's try to understand where did you get that formula from? Okay. There are two ways to do it. Let's try to see how to do it from the information we have seen so far. Okay. You are using something more sophisticated, but let's see how we do it using whatever we have seen so far. Okay. So what is the probability space here? Vertices in H. All possible configurations of vertices in H. Right? So that's for every vertex, either it's present or it's not present. Right? So it's 0, 1 to the n. Let's say omega is an element, then omega v is 1 if the vertex is present, and it's 0 if vertex is not present in H. So all possible omega are there are 2 to the n possible omegas. Agreed on this? For any omega, for any particular configuration, so say first vertex present, second not present, third present, fourth not present, so on. I pick a vector of a configuration. What is the probability of getting exactly that configuration? For every vertex, being present is 1 over 2, being not present is 1 over 2, and these are independent, because for every vertex I took the decision independently. Right? So it's 1 over 2 to the n. Fine? Good. Now let's define a random variable. That is number of vertices present as per the given omega, the given element. That is just number of ones in this vector. Right? Because omega 1, in omega you have 1 only for the vertex which are present and 0 otherwise. So x omega is just the number of ones in omega. Now I am asking, what is the expected number of vertices in H? What is that? That is just expectation of x, this random variable. Right? Because this random variable is exactly capturing the number of vertices in H. Right? So I want to compute the expectation of this random variable. And what is the simple formula? It's just sum over all the elements in the space, probability of that element omega times x of omega. But probability of every element is just the same, 1 over 2 to the n. Right? So it comes out, and then what are possibilities? So you can simplify. I don't want to go over like 2 to the n numbers here, right? So I simplify it and say that pick number of ones in omega. Okay, they can be 0, 1, 2, 3 up to n. And if there are k ones in omega, how many such omegas are there where you have k ones? N choose k. And for those n choose k, I am multiplying it with, I am kind of adding x omega, which is k. So it is n choose k times k. When you simplify it, you will get 2 to the n times n over 2, and that's why n over 2. Yeah. We can do it late in office hour if it's not clear. But I don't want to get into that right now. Okay? So this is one way to get n over 2. Now suppose I want to do this, the same thing with number of edges. Okay? Again, let's say same probability space. The first two things are same. Okay? Again, because you are deleting vertices still, but counting the expected number of edges remaining in H. So x omega will be number of edges present in H at omega. So previously it was easy for the vertices, right? You just count number of ones in the vector. But now, if I give you omega, that is what are the vertices present, how do you from that compute number of edges, like write a formula for that? You have to look at the vertex, what vertices are present and what were the edges between them. So defining this random variable and its value is not easy. Right? And then, if that is not easy, how would you compute its expectation? So this random variable is not helping us, like previously. So then there is a more powerful tool, which are called indicator random variables, and probably you were using that to compute n over 2 there. So indicator random variable is a binary random variable which takes value either 0 or 1. Okay? And you generally kind of define it for some event. So let's say A is an event, then indicator random variable for this event A, let's call x of A, is 1 when element is in A and 0 otherwise. Okay? So if I am rolling this dice, 6-sided dice, and suppose A is the event that I is divisible by 3, then xa of I will be 1 when I is 3 and 6 and otherwise 0. Because only 3 and 6 are in event A. The concept is clear? Okay? 1 if the element is in event, otherwise 0. Then its expectation is just the probability of A. Why? Because when you look at the formula, xa is either 1 or 0. It's 1 only when the y is in A. And in that case, you multiply it with the probability of y. So you are just summing up the probability of y when y is in the event. And that is exactly the probability of A. So expectation of such an indicator random variable of an event is just the probability of the event. Okay? Then there is linearity of expectation. So if you have two random variables, and if you sum them up, then expectation of the sum random variable is just the sum of the expectations. Okay, and again the proof is very simple. You are multiplying the probability with the sum, the random variable which is the sum, and then you can just split it, right? You have to raise your hand. I am assuming that this is very simple, okay? You have seen this before, okay? And you can extend this to say that if you have like a linear combination of random variables, and you take the expectation, that is just the corresponding linear combination of the expectations themselves. You can prove this using just the previous lemma inductively. Okay. Now let's go back to counting edges, computing the expectation for edges. Any ideas how should we do this? What kind of event should I look for? I want to count edges, I'm deleting vertices. That is half, that I know, right? But I want to count the edges. So let's focus on edges.
Each edge has two vertices.
Yeah.
So is that both of them or not?
Yeah, so let's define an event. AE is whether the edge is present. The event is when the edge is present in edge. So what's the probability of this event happening for a particular edge UV? So as he said, the edge can be present only if both the vertices of this edge are present. And because I deleted these two vertices independently, what is the probability that both are present? That is just the product of probability that first vertex U is present and second vertex V is present. And that's half times half, that's 1/4. Right? Now let's look at the indicator random variable for this event, XAE. And we just proved that expectation of this indicator random variable is just the probability of the event. In general, you can also say that this indicator random variable is just binary variable and it's 1 when the edge is present and 0 otherwise. And the expectation will turn out to be again 1/4. Okay? And if I want to compute the expected number of edges, then let's define X, which is a summation of these indicator random variables for all the edges. Because this individual variable is 1 when the edge E is present. So if I want to compute the number of edges present in edge, I should just take the summation of these variables. Right? Because for non-present edges, it's 0. For present edges, it's 1. So if I take the summation, I'm counting the number of edges in edge. Questions? And then I want to compute the expectation of X. By linearity of expectation, it's just the summation of expectation of each of these indicator random variables for every edge. Right? Because it's just kind of summing up the probability of all of these events for every edge. Because there are m edges, and for every event, the probability is 1/4, I get m/4. So there are 2 points here. One is you look at the problem and decide what kind of random variable you want to kind of design or look at. Okay? And second is using linearity of expectation. Okay? And when you said it's like n times 1/2, you are doing this. You are defining an indicator random variable for every vertex now, for the previous problem, whether the vertex is present or not. You look at the expectation is just 1/2, and then you sum up the expectations, that will be n/2. Okay? So it is important to set up the right set of random variables. Okay? You can also ask how many triangles are there. Okay, I'm not going to do that. Try and do it by yourself. It's fun. The same way. Okay, now you have to look at the three vertices. Okay, so now, so far we have seen quite a few examples. I mean, at least two initial examples of random algorithm. One was a QuickSort, the other was the multiplication of two matrices. In the first algorithm, I got a right answer for sure, but my running time was dependent on the randomization I used in the algorithm. Okay? So this type of algorithm, where the algorithm is always correct, but the running time is random. It depends on the randomness used in the algorithm. Those are called Las Vegas algorithm. And you can go and search why this name. Okay? It's a fun fact. Okay? The second type, which was the matrix multiplication, there the running time was n square. It was fixed. You pick a random vector, okay, multiply, do A times B times R, do C times R, and compare. So running time was deterministic, but the output was correct with some probability, incorrect with some probability. Okay, these are called Monte Carlo randomized algorithms, and sometimes you may have both. You may have running time and output both random. Okay, so there are three. So algorithm has, like, whenever you try to prove that algorithm is correct, you try to prove two things. It gives the output correctly, and its running time is something, so and so, worst case running time. Okay, so you may get randomization in both or one of the two, and based on that you have these three types of algorithms. Okay, now let's see how to do the analysis for these. So suppose I had a deterministic algorithm, and if I want to kind of see what is the worst case running time, I look at the running time of this algorithm for every possible input and take the max of it. That's my worst case running time of an algorithm. So deterministic quicksort, that's why the worst case running time is n square. Right? Because if the array is sorted, and if I'm taking always the first element, it will take n square time. And you can show that it cannot be more than that. Okay? For a randomized algorithm, now you are using some randomness. For even the fixed input, you are using some randomness. So suppose it's a kind of a first Las Vegas type of algorithm where you get the correct outcome, but the running time is random. It depends on the randomness that you use. So then, let's say Rx is a random variable that depends on the random bit used by the algorithm for the input X. Okay? Then I should be asking what is the expected running time? What is the expected value of R of X? So random variable is clear. It is capturing, so X is the input. Rx is capturing the running time of my algorithm on input X for a particular randomness that is used. Okay? So now, then I should be asking what is the expected running time of my algorithm for this input, which is E of expectation of R of X. And if I want to do the worst case analysis, I should be asking what is the worst expected running time over all possible inputs. Same as deterministic, right? There also we said, take all possible inputs. What is the worst running time of the algorithm? Instead of the running time, now we ask for expected running time. Because running time is not fixed for even the given input. It depends on the randomness used in the algorithm. For Monte Carlo algorithm, running time is fixed, but the output may be wrong with some probability. And you want to kind of minimize this probability. So you want to minimize the probability when the algorithm is wrong, so you want to maximize the probability that algorithm is right. Right? So let's say probability of X is the probability that the algorithm is correct on X, on input X. What is the worst performance of the algorithm? That is what is the kind of minimum probability, minimum over all possible inputs probability of X. Right? Because that's your worst performance. This is intuitive, right? I mean, did I confuse you? You want to maximize the probability of X, and that's why you are being harsh on yourself and asking, take all the inputs, all possible inputs. If probability of X is your probability of giving correct answer of your algorithm, by your algorithm, then look at the minimum. Be harsh on yourself and look at the minimum. That's your worst case performance. You will always do better than this for any input. Okay. So let's take a few more examples of why randomization helps. So suppose I want to kind of find one particular element, check whether I have array, and I want to check whether 10 is there in this array. Okay? But every time I check a cell, there is an adversary who will permute the array. The problem is clear. I have an array of numbers, n numbers. I want to check whether number 10 is there in this array. Okay? But every time I check a cell to see whether 10 is there, there is an adversary who would permute it. Now, if my algorithm is deterministic, how much time in the worst case it would take? An adversary know my algorithm, and it's deterministic. Sorry? Infinite. Because every time, because the adversary knows my algorithm, every time it knows which cell I'm going to check. And it will make sure that 10 does not sit there in that cell. And let's assume all the numbers are different. So it's not 10, 10, 10, 10. Now suppose I do it in a random way. I pick one element at random, uniformly at random, and check. Now what is the probability that I'll be able to, if there was a 10, I will be able to hit it in the first round? 1 over n. And then the adversary is going to permute it. And I'm going to repeat this. What is the expected running time before I stop? It's not. Yep.
Big O then?
Yep. Why?
Because it's expected to take n steps before you can, since you have a 1 over n probability every time. It's a, I don't know what the probability is, but it's one of those probabilities where the expected value is 1 over the amount of elements that you have.
I mean, you have to be careful when you do the analysis, okay? So you are right.
Yeah, there's a name for the type of variable distribution where every opportunity you have a 1 over n chance. I don't remember it.
So when do you go to the next round? When you fail in the first round. What is the probability you fail in the first round? So with 1 over n probability, you will do the one round. With n minus 1 over n times 1 over n probability, you will stop at the second round. Right? You are right, okay? But I'm just saying you have to be careful. It is order n, and try and compute it properly. Okay? Now, suppose I want to find an approximate median, okay? And in an array, approximate median is some number whose rank is between n over 4 and 3n over 4. Okay? If you try to do it deterministically, it's almost as difficult as doing a normal median. Okay? But if you want to do a randomized algorithm, then picking any number at random gives you a correct answer with half probability. Okay? And then you can probably, if n is 1,000,000, you can still kind of run it for say 100 times. Okay? And probably get an correct answer with 1 minus 1 over 2 to the 100 probability. Okay, so this is the power of randomization. So deterministic will take at least order n time. So if it was like million numbers, then you will take million time step, please. But with randomization, you will get a good answer, correct answer with 1 minus 1 over 2 to the 100 probability, like in 100 steps. Okay, so I wanted to also do randomized quicksort, but I'm not sure if I can finish it. But let me, yeah.
So how useful is expected running time? Because when you look at running time, you look at the upper bound.
Yeah, so as very valid point, right? When you say expected running time, that is kind of average of running time on all along the randomization that you have used. And very initially I said that even the randomized quicksort may take order n square time on any input with some tiny probability. Right? So we will see. So sometimes you may want to say, oh, well, I'm not happy with expected running time. I want something like order n log n with very, very high probability. Would you be happy with that? With say 99.99% probability. It will be order n log n. So then you do that kind of with high probability analysis, and we'll do that in the next lecture. Okay, so just recall, so randomized quicksort is you have n numbers, you uniformly pick a number uniformly at random among these n numbers, and then you compare it with every other number and see what are the numbers bigger than this, what are the numbers smaller than this, okay, and what are the numbers same as this. So you kind of divide the array into 3 subarrays, and then you recurse on the arrays which are smaller and bigger. So let's say for now all the numbers are different, just for simplicity. Okay, so you kind of whatever number you put, you are putting it in a right position. You put all the numbers smaller than this number on the left, all the numbers bigger than this number on the right. Okay. Okay. And now what we want to count is number of steps this algorithm takes, which is expected number of comparisons. Okay. So now if you want to do this analysis of this algorithm, you would want to kind of set up the probability space. What is the probability space? You have to kind of see in each round and in each level of recursion and each subarray, what choice did you make? Right? That's too big. Right? So like it's like analyzing this number of edges in that example. If you try to do it from a row probability space, it's too difficult. So it's important to set up right random variables. Okay, and see at the right events in the algorithm. Okay, and we will see in the next class how. Oh, sorry. Okay, yeah. Somehow I thought 10:30. Okay, okay. I have a lot of time. Good. Okay, so let's say A is my array of n elements. Okay, and let's say QA is the number of comparisons my quicksort does. I don't know what that is. I want to estimate QA. Okay, so first thing, this is a random variable because algorithm is random. It's using making these choices which pivot to pick at random. Okay. Now every time it makes, suppose it picks a pivot, right? And suppose its position is ith position in the array when it sorts, in the sorted array, right? So when it computes this numbers less than this element and numbers more than this element, let's say A left and A right are those two subarrays. Okay, and then we are going to recurse on that. Okay, so when I kind of applied my algorithm on A, and I pick this pivot, first I did n comparisons, or n minus 1, right, to check what are the smaller numbers, what are the bigger numbers, right? And then I'm going to recurse on the smaller numbers and recurse on the bigger numbers. So again, q of a left and q of a right. Okay, and this is for ith element, and I have to kind of multiply, because I'm looking at the expectation of q of a. What is the probability that I first pick the ith element, and then multiply this, because once I pick the ith element, I'm going to recurse on ai left and ai right. Let's say those are my arrays for the ith element, left and right. Okay, so the notations are clear? Okay, ai left is the smaller numbers when I pick the ith ranked element in A. What is ith ranked element? This element has position I in the sorted array. Okay. Okay, so since I'm picking any, so what is, in the first round, what is the probability that I pick any particular element? 1 over n, because I'm picking elements uniformly at random. So if I had n elements, picking any particular element, the probability of that is just 1 over n, equal, same. Okay? So this probability is 1 over n. I'm just repeating this formula by replacing this probability by 1 over n. Okay. Now remember, if I want to analyze this algorithm, I should be looking at the expected running time, and then look at all possible inputs and take the worst expected running time. That is the maximum possible expected running time. So let me define T of n by that number, which is the worst expected running time of my algorithm when the array has n elements. Okay. So again, this was my formula, right? So for a particular any given input A, now I am picking any given input array A, and I got this formula which is based on, I'm picking in the first round, I'm picking one element uniformly at random, and so it could be ranked the rank of that element could be anything from 1 to n. Okay, and so for every possibility, the array gets split into left and right, and then I recurse. So ask question if things are not clear at this point. What are QA I left, what are QA I right, and why this formula? Okay. So now if I want to take an expectation of this, then remember by linearity of expectation, when I replace this Q of A by this here, then I can push the expectation inside by linearity of expectation. So I get n, because there is no kind of randomness here, so n, plus this is a constant, and then I get expectation of QA I left, on expectation on the left array and expectation on the right array. So this expectation got pushed inside here because of the linearity of expectation. Why is that? Why I didn't, so here because n was a constant, I just wrote n. For a constant, the expectation is n because you are just choosing that number deterministically. Why didn't I write QAI left? Why did I put expectation here? Yeah. So, that's true. So that means I'm going to kind of run QuickSort on the left array, that randomized QuickSort. That means this quantity is not deterministic. It depends on the randomness that I use to sort that left array using randomized QuickSort. So I have to talk about, this is again a random variable, which is kind of capturing the running time of the QuickSort on the left subarray. Right? So that's why I have to talk about the expectation of that. And similarly, expectation of the right subarray. Is this point clear? Randomized QuickSort is a recursive algorithm. Okay? In the first round, you make a random choice, that is, pick an element at random. You find its right position in the sorted array. So say its position is I. Then on the left side, you have all the smaller elements. On the right side, all the bigger elements. But they may be unsorted. So you are going to apply again randomized QuickSort on the left subarray and the right subarray. Okay? So again going to make random choices. When you are kind of applying on the left subarray, you're again going to pick an element at random in the left subarray. Okay? So you have to talk about expected running time on the left subarray and expected running time on the right subarray. Okay. So how many elements can there be in the left subarray if the rank of my first pivot is I? Why? Exactly. That is the meaning of the rank of an element, right? It is at ith position in the sorted array. That means there are I minus 1 elements smaller than this element. And those are going to be in the left subarray. Right? So if Tn is capturing the kind of worst case running time on n elements, then here when I take the kind of max of this, it will be Ti minus 1. Because I am just going to do the worst case analysis again. Right? So this is the expected running time when my array size is I minus 1. And that is the array size of Ei left. Right? And this is on the right side, by the same logic, there will be n minus I elements. Right? So Tn minus I is the number of kind of the worst case analysis of the algorithm for the array of size n minus I. Okay. So if we put everything together, we want to do kind of worst case analysis of randomized QuickSort. So we are looking at T of n. So for any particular array, expected running time will be at most this formula. This is the formula that we are getting from here, the same formula. Right? And because the max, we are taking a max, which is T of n, and this holds for every A. So T of n is at most this. Because for every A, expectation of Q of A is at most this. So T of n is at most this formula. And do you recall what this formula is? Have you seen this formula somewhere? No? You have solved it actually. Homework 0. Last sub-problem in the first problem of homework 0. So you know how to solve this. Right? So T of 1 is 0. If there is only one element, you don't have to do any comparisons. Itself is a sorted array. That's the base case. And how did we we want to prove that this is order n log n. That's what was asked for, right? And you do it by induction and by guessing. So you assume that for every array less than n, it is, so for any array, any k less than n is say 2k log k, and then prove it for this, for the n size. So these are smaller than n. So you can plug in those formulas here. Okay, so that that finishes it. Any questions? So the important point here is that if we try to in general, when we run algorithms, I mean tossing coins and rolling dice is easy, right? But when we try to analyze algorithms, there is too many random bits we may be using. And then if you try to explicitly describe the probability space and try to compute each of probabilities of each of the events and try to do the analysis from there, it's very difficult. So that's why these random variables help a lot. Okay, and it's important to do a good job in selecting the random variables. Okay. Yeah.
Is there any reason to actually use randomized QuickSort, or is it just for the purposes of demonstration? Because I mean, since the expected running time of normal QuickSort is n log n, so.
No, what do you mean by expected running time of a normal QuickSort is n log n?
Like if you look at the, I don't think I can explain off the top of my head. That's what
I think you are talking about average running time.
That's what I meant to say.
Yeah, so that's why I wanted to make that difference between average running time and expected running time. But yeah, go ahead. Yeah.
So is there an actual, a practical benefit to doing something like that, to using the randomized algorithm?
Sometimes your input may be not as random as you think. Actually, things are not so random, and that is one question. How do you generate these random bits, right? So when you say average running time, you are assuming that the input is really random. Okay? In the sense that your input array is a random permutation. How true is that statement? Exactly. So when you do randomized QuickSort, you are actually permuting it in some sense. You are trying to make it random.
If you do the following, you take your initial input and
permute
it, and then give it to the regular QuickSort, it will do also n log.
But probably you will be using the same amount of randomness that you would use for randomized QuickSort. And random bits, generating random bits is a very, very, very interesting question. How would you generate random bits? Are your coins really unbiased? How would you flip coins in in computer? It's a whole field in itself, research field. Okay. So you try to use nature, yeah.
So basically, like usual QuickSort, it's possible to adversarially choose bad inputs, which is what would be taken care of with this.
Sure, but his question was are the inputs that you get from whatever application you are trying to run adversarial? Right? It may not be adversarial, but it may not be as random as you think. And as Chandra said, that another way to do is that you first permute the input. Okay? Pick a random permutation of the input and then apply deterministic quicksort. That is same as kind of running, it will do n log n. But the amount of random bit you will use is kind of same as a randomized quicksort. The next question is, how do you get the random bits? Because if you don't have random bits, how will you kind of run a randomized algorithm? Okay? And probably you don't get exactly random bits. You get pseudo-random bits. Okay, and that is a very interesting question and a research question. Okay, I also have a slick analysis, but you can try and go over this, and if you have questions, you can ask, and if I have next lecture, if I have time, I'll go over it. So I didn't start it because I knew that I won't be able to finish it.
Where does this come from?
Good. So when you pick a pivot in the first round, what do you do?
Just randomly choose the one from those.
And then what do you do after that? So once
compare. Yeah.
How many elements with which you compare it?
n-1.
Exactly. That's n. So because we are counting the number of comparisons, right? So as soon as you pick a pivot, before you go to next level of recursion, you do n comparisons. And that's this n.
And for each recursion one, we should do the same thing.
Yeah, that's why this is in the Q of A. So when you expand this, you will get here I minus 1 when you open this up.
So in the normal one, I mean, without a randomization, we needn't to have this one, just and this one.
Correct.
But in the randomization, we need to
Yeah,
add
so you
some
have
probability to.
Yes, so you have this summation because your pivot that you choose may have any rank or any possible rank, right? Because you pick the pivot at random, right? It could be the first element, it could be the second element. You don't know, right? In the sorted array.
Got it. Thank you.
Yeah.
So what is the worst case of this sorting? For example, I want to sort the array from the smallest to the largest, but now what I have is from largest to the smallest. Is that the worst case, or?
Good question. You should think about it. For the deterministic quicksort, we know what is the worst case.
Okay.
Right? What is the worst case in the randomized quicksort? Think about it, and we can talk about it in the next lecture.
Okay. Okay.
After the next lecture, or before the next lecture.
The randomized is just in deterministic, you choose the pivot one by one from